¿no? Ok, entonces ya, muy buenas tardes a todos y bienvenidos al coloquio semanal del Instituto de Ciencias Físicas de la UNAM en Cuernavaca. Nuestro invitado es el Dr. Robert Oeckl y déjenme decir algunas pocas palabras sobre su vida. Robert estudió física y matemática en la Universidad de Bonn, en Alemania. Hizo su maestría en la Universidad de Wisconsin, en Estados Unidos, y su doctorado en la Universidad de Cambridge, en Inglaterra. Hizo después un postdoc en el Centro de Physique Théorique en Marsella, en Francia, y desde 2004 es investigador en el Instituto de Matemáticas de la UNAM en Morelia. De 2013 a 2014 fue también investigador visitante en la Universidad de Erlangen en Alemania. Sus principales líneas de investigación son la gravedad cuántica, los fundamentos de la teoría cuántica, la teoría cuántica de campos y los grupos cuánticos. Robert, muchas gracias por aceptar nuestra invitación hoy y visitarnos por lo menos virtualmente, y ya, esperamos a tu conferencia.
Muchas gracias, Tomás, por la invitación. Es un placer estar ahí presente, aunque virtualmente, en el Instituto de Ciencias Físicas. Y bueno, les voy a platicar algo sobre gravedad cuántica. Voy a compartir ahora mi presentación. Un momento. Ok, espero que pueden ver la presentación.
Sí, todo muy bien.
Ok, entonces, bueno, de hecho una pregunta era si hablo en inglés o en español, pero creo que tal vez sea mejor que hablo en inglés, pero obviamente pueden hacerme cualquier pregunta en español. So I'll switch to English now. So I'm going to tell you something about quantum gravity, but the title of my talk is not just quantum gravity, but it's predictions in quantum gravity. And I hope during the course of the talk will become more clear why I put predictions there in such a prominent place in the title of the talk. There's also, you can see on the page here on the bottom, two papers in particular that are referenced and that are of particular importance for what I'm going to tell you. Okay, so let's start. The first obvious question is why quantum gravity, and what is this about? So this is just to remind you. In fact, this slide, in fact, is in Spanish, but okay, should be fine. That in modern theoretical physics, as concerns fundamental theoretical physics, fundamental theories, we really have two different pillars of our edifice of fundamental theoretical physics, which on the one hand is quantum theory, and more particularly the standard model of elementary particle physics, which is on the right-hand side here, which describes matter at small scale or also intermediate scales, and forces, electromagnetic, weak, and nuclear, and strong. On the other hand, we have general relativity, which describes gravity and together with space and time, and we use it to describe the large-scale structure of the universe and processes in the universe as a whole. However, these two pillars so far have not been brought together into one theory that could explain all these phenomena together. And this is precisely what quantum gravity is supposed to be. So this is supposed to be a theory that contains both the standard model of particle physics and general relativity. Now, of course, for the description of many phenomena, we don't need quantum theory of gravity. I mean, we are fine with either the standard model of particle physics or general relativity, but increasingly there are many phenomena where gravity is strong and where also quantum theory is important, that become accessible to observation and that play a more and more important role, particularly in astrophysics, astronomy, and cosmology. So just to illustrate this, I put here this kind of illustration of the history of the universe. And on the right-hand side, this picture that you've all certainly seen recently, that was the first picture of a black hole. So black holes are obviously precisely an object of interest, and to describe them correctly, especially with regards to the interaction with matter, which is described by quantum theory, it would be essential to have a quantum theory of gravity. Now, when I talk about this, and well, as you all know, we don't have a quantum theory of gravity. Why is that? Because you could think, well, I mean, general relativity is 100 years old already, a bit more now, and quantum theory will also soon be 100 years old. Its basis its foundations were laid in the late 1920s. So why, after all this time, we have not managed to bring the two together into a unified framework? So, if you heard other people talking about this, you will have heard probably different opinions on that and different reasons. One, obviously, that technically this is a formidable challenge. But what I would like to emphasize today is that there are also conceptual obstacles which are very important. So in particular, the standard formulation of quantum theory, that's the type of quantum theory that's in quantum mechanics textbooks and also in quantum field theory textbooks, requires a classical notion of space-time, and in particular, a notion of time is very important. And that has to do with the fact that when you talk about preparations, measurements, and things like that in quantum theory, the way you extract predictions depends on the temporal order of the different things you're doing, like preparing, measuring, and so on. Now, in a general relativistic setting, where a priori you don't know the metrics of space-time, so you don't know a priori how what is time and what is space, then you don't have this. If you don't have this information, you can't apply quantum theory, at least not in its standard formulation. What you can do is you can try to restrict, if you look at a phenomenon that involves quantum gravity, or that you would like to describe in a way using something like a quantum theory of gravity, what you can then try to do is restrict the measurements that you're doing and preparations to regions of space-time that are well described by classical physics, and whether the space-time metric is fixed. So, but first, let us go to forget about gravity and think about quantum field theory, where how is measurement done in quantum field theory? So here's a space-time diagram, time going up, space to the right. So basically, the type of measurement is very simple in the sense that you're thinking of preparing some initial state, generally in terms of like certain incoming particles. Then you have interactions, and at late time, you're looking at what comes out from your interactions, the outgoing particles, and make a measurement at a late time. So you describe this by transition amplitude and associated transition probabilities. And then in order to deal with interaction, there's another thing that you have to do. You have to think of the preparation at the initial time as being far removed into the past, and the measurement as moved to the infinite future. So you're doing an asymptotic limit, and then this transition amplitude becomes what is called as the Ace matrix in quantum field theory. Okay, so this is a picture more or less familiar to most, I think. Now, if you wanted to consider a situation where quantum gravity is important, where in space-time, in some region of space-time, gravity becomes strong, and you also want to consider quantum effects. So in particular, the metric of space-time will not be a flat Minkowski metric anymore. It will be something complicated. And in fact, in particular, it will not be something fixed. That's important. We are only concerned with quantum gravity if we think of the metric of space-time itself as subject to quantum fluctuations. Now, as I said, if we do this within the standard formulation of quantum theory, then we'd have to ensure that around this quantum gravity region, there's space-time can be described by a fixed classical geometry, fixed classical metric. Now, as I reminded you on the previous slide, if we in quantum field theory, if we want to describe interactions, we need generally to do this using perturbation theory, and that would be the same situation here, because the metric outside of this quantum gravity region will be fixed, and so we'd have strong gravity only inside a confined space-time region. So to deal with the situation that we fix it on the outside, we'd have to perturb about this fixed outside metric towards the inside. Now, if you try to do this straightforwardly and treat quantum gravity as a quantum field theory, then this doesn't work, as we well know. The perturbation theory breaks down. It's not renormalizable, as one would say. But the question here is, can this kind of picture work even in principle? Is it in principle feasible to think of these quantum gravity situations in that way, where you have a fixed metric everywhere outside, including all the time in space far away from the quantum gravity region? And in fact, what I'm going to show you today is an example, but one could also think of other similar examples where you can see explicitly that this kind of picture doesn't work, and also why this doesn't work. So again, the thing I want to take away from here, from these two slides, is here what you are having. You are determining what you're predicting is that you have some initial state, let's say particles, and you are asking how probable is it to have some final configuration of particles or other objects at a late time. Okay, so let's look at an example. This is a so-called black hole bounce. I'll say a bit more about this. And in particular, so on the one hand, I want to show you that there's a problem with the kind of traditional approach to describing physics with the standard formulation of quantum theory in this example. And on the other hand, I want to show how with a different approach, I'll say more about that in a moment, or we can make progress and possibly make predictions in such a setting. Okay, so what's this black hole bounce model? Okay, so here is a diagram of a black hole. It's a so-called Penrose diagram. So if you're not so familiar with those diagrams, that's not so important. What's important here, it's a space-time diagram. So time goes up, space goes to the right. Here you should think of space, you should think of that as a kind of spherically symmetric situation. And so to the right is the radial distance from the center, which is the line here to the left. Now, what's happening? Well, we are in flat space-time, nothing is happening, but then from far away comes in a shell of matter. So you can think of this as matter literally in a spherical configuration, but moving towards the center at the speed of light. And this is a shell that's infinitely thin. So you can think of this either as some kind of ultra-relativistic matter or light. It's not so important what exactly it is. So what happens is the same that happens when a star collapses. We are forming a black hole. So the red line is this colored collapsing matter. And then a so-called event horizon forms, which is in the interior is a space-time region where nothing can escape. I mean, as you know, even light cannot escape from a black hole. So if you are beyond this dashed line here, then everything, including light, falls into the black hole, and you have a so-called singularity there. Again, the exact details of this diagram are not so important. Okay, so this is formation of a black hole by a collapsing null shell. That's how this is called. And there's just one physical parameter we need for this very, very simple model of black hole formation, namely the mass of this infalling matter. Okay. Now, let's suppose that quantum gravity becomes relevant so that this description of the formation of the black hole, which is really based on classical general relativity, doesn't work anymore if the space-time curvature becomes large. So this is kind of this bluish region here in this diagram. And that this will prevent the formation of a singularity. So anyway, singularity is a point where general relativity doesn't make sense anymore. So where we definitely know that this classical theory, general relativity, has to break down. So it's reasonable to think of this region where quantum gravity becomes important as a region where actually there's no singularity. But in fact, there isn't even a well-defined space-time metric if you take quantum gravity seriously. Now, let's suppose that what happens is that something like a tunneling occurs. That is, a situation occurs where basically we again have a black hole, except that it's time reverse. That's called a white hole. Okay, so that we are tunneling from this black hole situation to a white hole situation, which means that again we have this quantum gravity region, but then the opposite happens, or the same happens, but in time reversal, which means that suddenly it's like an explosion and a null shell will emanate from this former black hole, which no longer is a black hole, but what remains is again just flat space. Okay, so this is an idea that has been around for some time, that quantum gravity could induce this happening, and that's called a black hole bounce. Now, how realistic or not this actually is, and if something like this actually happens or doesn't, of course, will require us to have a concrete model of quantum gravity. And yeah, so there's certain approaches to quantum gravity, but we don't have really an established theory. So we don't know if this happens or not. But what's interesting to us here today isn't if that's really the realistic thing that's happening, but to see this as an example of talking about quantum gravity, and more importantly, talking about measurements in quantum gravity and predictions in quantum gravity. Okay, so we are supposing that that this happens, that black hole forms, but then we have a tunneling to a white hole. And so if we describe space-time as a whole, we can bring this in a single diagram here. Again, time goes up. The left line here is the center. And what happens now, so this massive shell comes in and then later comes out again outside. Now, the important thing here is that outside, we can, so these two pieces of space-time, the black hole and the white hole space-time, they can also actually be matched outside if you're far enough away from this center of the black hole and white hole, then this can be described perfectly well by classical general relativity. So what you have to do, of course, this blue region cannot be described. This is where normally you would have the singularity and then the end of it. Okay, but we are supposing that we have this tunneling process, and that outside we can describe this with a classical space-time metric. And then it turns out that there's a one-parameter family of such space-times that you can construct, which are described by one single parameter, which is a time. So it's called the bounce time. So how can we think about this bounce time? Well, one way to think about it is supposing that this incoming mass shell really collapses to the radius 0 center, and then a certain time elapses, and then it comes out again. Of course, this isn't really what's happening here, because what's happening here is something that can only be described by quantum gravity, and that certainly will not be describable in terms of a classical metric. But in any way, as a way to parameterize, this is perfectly valid. So there's a one-parameter family of these spacetimes, where, of course, the other parameter that we were mentioning already is the mass, the shell mass. So we have two parameters now. So we have the shell mass and we have the bounce time. Now, the other thing I would like to tell you about here is in this diagram. So this dotted line here would be an observer trajectory. So suppose you're in a little spaceship and you are at a certain distance from this center, radius 0 center, and you're just sitting there. And so what's happening? Well, you are in empty space, and suddenly from one side, there's passing this mass shell is passing you and converging to form the black. And then we have this tunneling, and then at a later time you will see it comes back, right? So the exploding mass shell from the white hole comes back and goes away to infinity, basically. So you can probe this in this way. You can probe this space-time geometry. So you just need basically a clock. You're sitting there and you're waiting, and you also know how far you're away from radius 0. And you're sitting there and starting your clock when this passes, and then when the mass shell comes back, you stop your clock. And then you can use the time that you see on your clock. Of course, you have to take into account how far away you are from radius 0. The further away, the longer will be the time you measure on the clock. But you can do then a little calculation and use the time on your clock to recover this bounce time precisely and measure this bounce time. So it's something that you can actually measure here. So by the way, if you have questions that something I don't explain it well, or you want to know something, please feel free to interrupt me. Okay, so this is this bouncing black hole situation. So what's interesting about this, if you think about this, and if you think about this, the previous slides I showed you about the S matrix and the measurement, how you do it in quantum field theory, and also what you could expect to measure in quantum gravity if you're measuring far away from the quantum gravity region. Then what we were saying is that if you want to make such a measurement, you need to suppose that spacetime is classical and fixed far away from the interaction region. And if you look at this picture, that seems to be the case, because I was telling you, while spacetime is classical here and is just a solution of general relativity as long as you are outside here. But I was also telling you about the bounce time, and that this diagram really represents a family of different spacetimes where which are parameterized by this bounce time. So even they are all classical and basically all look the same, like flat space outside here. There's a difference, and the difference is the thing that this observer can measure here using his clock. So if you think about this in terms of the usual scattering picture, you would say, well, what I'm shooting in some particles, and then I'm asking how probable is that certain other particles or particles with certain other momenta come out at late time. But if you look at this picture here, if you are thinking in these terms, then you cannot at all determine the bounce time. The bounce time doesn't have anything to do with the particles coming in and going out in the sense that they will have different quantum numbers, and this is what you want to measure, or different momenta or whatever. What comes in, this mass shell, and what goes out is always the same. The thing that changes is you can only see that if you are outside and you are measuring on your clock. And what you're measuring is not what are the particles that come in and go out, but you're measuring this time, and you're measuring how the spacetime in the exterior, even though it's classical, is modified depending on what this parameter is, the bounce time. So that means that this picture that I was showing you previously here, I mean, even this one and even this one doesn't work. Okay, this is not a measurement where you prepare some initial state and then you're looking what kind of final state comes out. It's a measurement where you're measuring something about the space-time itself, and which is not neither in the initial nor in the final state here, viewed from a traditional point of view. So how can we do such a measurement? How can we describe such a measurement even in principle? Okay, it's not prepare, measure, observe. That's not working here. So there have been advances in the last years in quantum information theory and quantum foundations that have given us a way to think about quantum theory, which is a more general and more powerful. And the way I like to describe this is in terms of what I call the positive formalism. And this does away with this problem of the standard formulation that you need to know in advance what is the temporal order of measuring, preparing, and so on. So the hope is that with this new understanding of quantum theory, it could be possible to actually reach a workable theory of quantum gravity. But what I'm going to tell you now is not a theory of quantum gravity, because I don't have one, nobody has one still, but how the measurement can be how this situation and the measurement of the bounce time can be described in principle in this situation. So, okay, so I'll tell you a little bit about this positive formalism. So the most important thing that you have to think about in this setting is the notions of measurements, of observations, interventions, and so on. So, for example, you again in the usual picture, you would think about preparing some state. So here, this is symbolized by having some apparatus where you have a switch. So this can be in position A or B, and this would correspond to different states. And then later you make an observation. For example, here's then a measurement device that has a light which shows green. Now, what is important here is that we think of these measurements, observations, interventions, and so on, not in a temporally ordered way, but as distributed in space and time in a more general way. I'll come back to that. And what we want to predict is, in general, is not given. So in this situation, you would think, okay, so given that I put the switch in position A, how probable is it that the light will be green? And so here, there's a kind of pictorial representation of this probability. So what you should know is that I'm drawing here some diagrams, but in fact, these diagrams can be given a mathematical meaning, an algebraic meaning, if you want. And from these algebraic objects that are represented by the diagrams, you can extract, in this case, the probability for something to happen. Okay, so here, as I said, we're interested. We would say, okay, so how probable is it that the green light, that the light is green? So we are supposing here that this light can have different colors, green or red. How probable is that, given that we had put the switch in position A? And so in the standard formulation of quantum theory, the answer will be corresponding to a combination of these diagrams. I'm not going into the technical details. Later in the talk, I will get a little bit more into technical details, but what I want to transmit here is the conceptual idea. Okay, so this probability is something that you can extract from combining these objects, which, as I said, are algebraic objects that correspond to these diagrams. So in particular, you get a number. And in the positive formalism, when you talk about probabilities, you generally need two numbers. So you need one number that corresponds to your experimental setup and everything that you have prepared. So what is that? Well, you have two devices. On one device, you put your switch in position A, and the other device is a light, and that's it. And then, so this is the measurement setup. In the measurement setup, you're not yet specifying what is the color of the light that you're going to observe, because that is part of the question you're asking. So you have two inputs. One is the setup and everything you know already about the experiment, and the other one is the setup together with the outcomes you're selecting and you are asking your question about. So the question is about probability of the light being green, and that's represented here. So it turns out that these probabilities can always be represented by quotients as shown in this example, where this is one diagram or one number that is extracted from algebraic objects that correspond to this diagram, and here is another one. Now, another thing is that what we want to think of is that these measurements, interventions, and so on, they happen in space-time. And to describe this in a local fashion, we cut up space-time into space-time regions. So like in this diagram here, so again, this time goes up, this is space. So we have one device in each region, or no device in some region, to be able to identify where this process takes place. And so in general, we talk about these measurements and so on as call them processes. And this, we call this a composition of processes, and they're associated to space-time regions, and we compose them by gluing together these space-time regions. That one way you can think about it. Where are you gluing them? Well, this is hypersurfaces where they touch, right? Where these regions touch. And on this hypersurface, what we'll have is states, like the states of the Hilbert space that we're usually thinking of in quantum theory, except here, we don't have just one Hilbert space, but we can have one for each of these hypersurfaces. So what do these states parameterize or represent? They represent interactions between the space-time regions, physical signals that travel from one to the other. Okay. Now it's let's say a bit abstracted view of quantum theory and of this generalization, which is the positive formalism. So to come back to the S-matrix picture of quantum field theory and to put this in a more familiar context. So in that case, remember this diagram, I put some boxes on this diagram here, namely 3 boxes corresponding to these 3 space-time regions. The first one is the space-time region where you prepare, where are the incoming particles, if you want. And I put initial state here. Then there's a region where the interaction happens, but you're not intervening here at all. You're not having any device in this region, just physics happens. But this is where your interactions happen if you are thinking of quantum field theory. And so the symbol I put here is this box, this crossed out box, which means that it's just the system is freely evolving. And then you have a delay time. You're making a measurement and detecting a final state. Now, if I put this as on this slide here in this form, where I just put all the boxes together, then this looks like this. So basically, you should look at the numerator here, because again, this will become a quotient of 2 numbers. So the numerator corresponds to these boxes here, namely the initial state, which I put here in. This signifies the evolution here in the intermediate time, and then the final state, which is the out state. So usually in quantum theory, and so this is where the difference really becomes important between the standard formulation and the positive formalism. You would just look at these boxes on the top. So you're just thinking about, you have an initial state, you evolve with interactions, you have a final state, and that's it. And your calculation of the probabilities or the corresponding scattering amplitudes, which come out of, which are expressed in terms of, if you want, probability densities, just involve these 3 boxes at the top. Okay. But before I was telling you, well, in the positive formalism, you have 2 copies. You have your experimental setup, and you have what you're asking for. So what is this in this situation? Well, in this situation, what you're fixing is, well, of course, the interaction, but you're also fixing your initial state. What you're not fixing is the out state, or what you want to observe at the end. So your setup corresponds to preparing your initial state and evolving, and that's it, nothing more. So that's why I put a question mark in this box. So this is a box that represents the final state, but in your measurement setup, the final state is undetermined. So this is why there's a question mark. And this question mark, it doesn't mean we don't know what this is. We know perfectly well what this box means algebraically. Okay, you can think of this as summing over all possible final states. Okay, that's one way to think about it. And then in the positive formalism will tell you now, oh, okay, so your probability for finding these outgoing particles in out given the incoming particles in is this quotient. So why, if you look in your textbook or do your usual S matrix calculation, don't you see the quotient? Well, the reason is that in this case, the denominator here has the value 1. Okay, so which usually you would interpret in saying that the probability that something comes out if I make a preparation is 1. Okay. Now, the important thing here to know, and why do we talk about these quotients, is that in general, the reason that the numerator itself is a probability has to do with the fact that we have a fixed temporal order. In the moment that you don't have this order anymore, the way that you normalize things to make sure that the denominator is 1 here doesn't work anymore. So you need to divide out explicitly by this denominator. And so this is a very important conceptual step in going to the positive formalism, that your probabilities will in general be quotients as illustrated here. And if you do that, then it turns out that you can now really throw away the predetermined temporal order and make probabilistic predictions, even if those boxes are not ordered in this temporal way, but ordered are distributed in space-time in a much more general way. And even in situations where you wouldn't a priori know what is space and time. Now, what we're interested in is now, and this is the last part of the talk. So here I will tell you a little bit about how concretely you use the positive formalism to talk now in this concrete example about this bounce time. So what we want to do, we want to measure this bounce time. So how do we do this? Of course, to do that, we would need a theory of quantum gravity, which describes how the physics in the interior here, where we have this forming black hole and bouncing to white hole, right? Now we don't have that, but we shall assume what we want to know is now what kind of objects do we need to construct to if we want such a quantum theory of gravity, okay? And how can we use those objects then to express the measurement of the bounce time? Okay, so if we think about these boxes again, so in the interior here, we are not, of course, we can't go into this region. I mean, that's the high curvature region where we'd be destroyed if we go too close to the black hole, right? So we stay outside. Remember that. So this is the observer, which the trajectory of the observer, which was the dotted line in the previous diagram. Right, it's not here anymore, but so it's here. This dotted line. This is where we're sitting with our measurement device, which is really just a clock. But what are the variables? We have the parameters. Well, we have the mass of the shell, and we have this bounce time that we are measuring by comparing when the shell comes in and when the shell goes out. And whereas here we are not doing anything. So Okay, so the boxes look like this now. So in the interior, nothing happens. And in the exterior, what's happening? Well, as we said, we have two variables, the mass and the bounce time. So what kind of probability can we ask now? So for example, we can ask, how probable is it that the bounce time is in a certain time interval? Okay, I'll call this τ1, τ2. So how probable is that the bounce time is in this interval? The other variable that we have to fix to do this is, of course, the mass. So we are supposing that we are asking this question given a fixed shell mass. The quotient that I was talking about looks now like this. So in the denominator, we have this quantum gravity region, and in the exterior, we fix the mass of the mass shell, but we don't know anything about the bounce time. So the bounce time is open, is arbitrary, okay? And then the question we are asking is, well, on top of knowing what the shell mass is, we are asking what's the probability that the bounce time is in this interval. So it looks like this. So this is directly analogous to this picture here, to this quotient here, and also to this quotient here, okay? Now, as I said before, we associate these boxes or these processes with space-time region, and here we just have two space-time regions. The exterior region that's well described by classical general relativity, it's called X here, and the interior region where we think that quantum physics becomes important, and quantum gravity, in fact, which is Q. And the hypersurface that separates the two is sigma here. Okay. Now on the bottom here, there's a more formal way to write this quotient here, which also involves the bounce time, involves the shell mass, which is called M0 here, and then Bx is the algebraic object that corresponds to this box. Okay, I'll not say much more about what this actually means, but these double brackets here refer that we are making a composition of two boxes. So one to the left, then there's a comma, and then there's the one to the right. Okay, and all these things will have a well-defined mathematical meaning, but which I'll mention a little bit later. But the important thing is that we have this quotient, and this is what we want to calculate. Okay, this quotient. And of course, this box with the Q is something that will require a knowledge of the quantum theory of gravity if we actually wanted to determine what this is. Now, the one remarkable thing about this positive formalism is that it can also be used to describe classical physics. And in the classical case, what would happen is that we would have, for each shell mass, so suppose we don't have general relativity, but we have a classical theory of gravity which modifies general relativity in such a way that this bounce scenario of black hole, white hole bounce is a physical solution of this theory. So then this theory would tell us what is the bounce time given that I have a fixed shell mass. And then I can plug this in. Okay, I will not, I mean, there are some formulas on these slides now, but I'll not explain them. I will just mention that what is important here is in the classical theory, the important structure is the classical phase space. But here the space just has two parameters, which is the mass and this bounce time. And you can think of what happens at the boundary, the mathematical object that allows you to glue these two processes together is here a space of statistical distributions on phase space. And then if you fix the bounce time, this just corresponds to the delta function. And if you fix the shell mass, that corresponds to the delta function. If you fix the shell mass, and in addition, want to have the bounce time in a certain interval, then this would correspond to a characteristic function of this interval on the bounce time. Okay, I just flashed some formulas here, which is not important, the details, but then you can write this as an integral, and what the interior region does, it enforces this bounce time that this classical model of yours gives you, and then at the end you can plug in these objects here and find that what you get is exactly what you're expecting, is namely that the probability is either 1 if the bounce time that this classical model gives you is in the interval that you're asking for, or otherwise it's 0. Okay, so no surprise. The only important thing here I wanted to tell you is that the very same structure of the positive formalism and of the composition of the object that corresponds to these boxes works both in classical and quantum theory. Of course, the content of these boxes, so to speak, is different. In one case, we have statistical distributions and integrals, and in the quantum case, we have Hilbert spaces and spaces of density matrices. Okay, so in the quantum theory, I'll not explain this in detail, I'll just flash this. What's important is you need so you have this classical space-time region outside, and inside you have a quantum region. So how do you bring together classical and quantum? Well, one well-developed tool for that is coherent states, which you might know perhaps very well from a different area of application, like, for example, quantum optics, or play a role in many different areas of quantum physics. So if you have a notion of coherent state, you can think of having coherent state that approximate these classical solutions on the outside. And since they are just parameterized by 2 parameters, you have a 2-parameter family of coherent state. If you have a completeness relation that involves these coherent states, where you just integrate over the masses and the time, and there's some function here that makes this completeness relation work, then for those of you who are familiar with this, you can think of this giving you a positive operator valued measure of your quantum system, and that allows you then to quantize, so to speak, classical distributions on phase space and convert them to quantum operators, which corresponds to mixed states in your quantum theory that represent these classical states, which are your phase-space distribution. So you plug this into this integral, and you are integrating over these. You can think of this as a projection operator. So it's a family of projection operator parameterized by this mass parameter and bounce time parameter, and you integrate, and so you're getting you can think of this as a linear combination of projectors, except it's not a sum but an integral, but it's essentially the same thing. So you get an operator here. And so this operator is what in your quantum theory now represents your classical input, which in our case of interest will be, in fact, will be exactly these same functions here. So on the one hand, remember in the denominator what you want to do. Here, you're fixing the mass, the two of the shell, but you're leaving open the bounce time, and here you're fixing the mass and you're fixing the bounce time to be in an interval. So if you plug these classical distributions into this formula, sorry, this one here, then you get corresponding operators for your quantum theory, or your quantum gravity theory, and then it turns out you can then describe the amplitude of your quantum theory in this interior region where you have this black hole to white hole transition for arbitrary states on the boundary, which is this boundary between the quantum and the classical region, by this formula, which you can derive from the previous formula. Again, it's not important what this exactly means here. If you want, you can ask me about that later. The important thing is that you get a well-defined formula, and then with that you can in particular calculate. So in the numerator, inserting the condition that you fix the bounce time and you fix the mass and you fix the bounce time in an interval, and the denominator you fix the mass but you leave open the bounce time. Then you get a mathematical expression that involves these amplitudes of your quantum gravity theory, and that gives you exactly the probability you're looking for. So again, it's not so important that you're getting all the details here. What I really wanted to do is just give you an example and kind of give you a flavor of how, in principle, using this positive formalism, you can do this kind of calculation if you have a candidate quantum gravity theory. Okay, let me stop here, and thank you for listening.
Yeah, Robert, thank you very much for this very interesting talk. Thank you, thank you. Are there comments, questions from the audience? So Sebastian already wrote a question in the chat. I don't know, Sebastian, you would like to, yeah.
Yes, thank you. So maybe it's a totally the question, but when you present the classical part of the bouncing black holes, so it was at the middle of the presentation. So you was mentioning that it was like a reverting the time, and it was a property more of the space-time than just a kind of measurement. And I was just thinking, probably stupid, but if I have a system with a given charge and parity, the fact that we reverse the time should have an effect on the CPT symmetry conservation. So we have to change the CP symmetry of the system, or there is no problem here?
Sorry, so you're talking about the quantum theory or the classical?
In fact, it was inside the classical part. So it was a part where we have a quantum part and a classical one. You show to us the trajectory, the path of an observer.
The trajectory of the observer.
Yeah, exactly this one. Yeah, exactly. And so here, if my observer is a system with a CPT or CP symmetry, so do there is any need to change something in the CP symmetry when you have the time reverse here?
However you want to eat.
When you compare this measurement with the other measurement in the later?
Yeah.
No. Okay. So So there are different things to say about. So the model as it's presented here is of course extremely simple. And we just have two parameters, and there's no issue with any CP symmetry. But of course, I guess your question is really if we're looking at a similar picture in a more complicated situation, right, where there are more degrees of freedom. Because of course, this simple example is really meant as an example, but it's an example for a class of situations that we could consider that all look kind of similar, where you have initially, we could also think about a black hole that forms and that evaporates, because we already know that by quantum theory that it has to evaporate. So, or any process where we have a strong gravity regime with that's also quantum, but which is temporarily confined, right? And then always the kind of picture we would have to look at would look kind of similar to this kind of picture. Of course, there would be more parameters. Okay, so so back to your question. So if we think of this observer now as being some perhaps more complicated quantum system that has certain transformation properties under CP symmetry, then so here in this picture, there wouldn't be any, you wouldn't apply that. I mean, in the region where this observer travels, space-time just looks classical. And there's no reversal of anything. The thing that's reversed is the system here that goes in and that comes out, but not the observer.
Okay.
So you could ask, for example, so given maybe this is something more complicated, not just a mass shell, or it's some matter that has spin or something. And now if you compare this incoming matter with the outcoming matter, then you can of course ask, should I think of this outcoming matter as some kind of CPT reversal of what comes in, or and then indeed you would have to think about that, and perhaps you would need to apply a transformation of that type to this incoming and outgoing matter. Yeah.
Thank you.
But of course that would depend on more details of your model that you're setting up. But yes, yeah.
Thank you, Robert.
Okay. Are there further comments, questions from the audience? Maybe I have a question related to this figure. Can I tune the parameter of the bouncing black hole, which is just tau, in such a way that the observer trajectory passes not only in the classical space-time regime, but also enters in the quantum gravity region?
So here the idea is that we are deliberately placing the observer so far away that this cannot happen. So we have deliberately avoided that by explicitly placing the observer far away. So if the observer was closer and something like you were describing could happen, then of course everything becomes more complicated, and then we'd have to think about the observer in a different way, because the observer would pass possibly through a quantum gravity region. So to keep it simple, we are avoiding this here.
Okay. Okay. Would the observer trajectory change abruptly as these red trajectories which you draw there? Yes.
Yeah. In fact, I mean, I was not. I didn't want to go into those details, but of course, yeah. It's since this mass shell is really is mass that's concentrated, so you can think of this as some kind of delta function thing. If you integrate it a bit, then it's not a delta function anymore. But if you take it at face value, it's like a delta function. So it will instantaneously, non-continuously modify the space-time metric near the observer, and which would then make the observer. So in fact, if you think about it, so the region down here before there's this shell coming in is this is just really flat Minkowski space, so nothing happens, and then the shell comes in, and then the observer is suddenly in a Schwarzschild metric, because there's there's matter around the center, and the observer is outside, so it's in the outer region of a Schwarzschild metric, and that of course, since there's mass in the center, and it has an attractive force, so if the observer is inertial and has no rocket engine or something, then the observer would slowly start to move towards the center, towards the black hole, but slowly. I mean, of course, depending on the distance, right? And then at a later time, when this shell comes back, then the observer is moving in, and then it comes back, it's in flat space-time again, and then would just be inertial again. I mean, with respect to the original space-time, yeah. And so to take into account, so there are two ways to take this into account. One is simply to say, well, okay, that's just how it is, because the important thing is that the observer, I mean, doesn't fall into the black hole, right? So if the observer is sufficiently far away, then even if there's a small drift, it will not make the observer fall in. I mean, the shell will come back long before. So either you can do that, and or you could say, okay, so now the observer is switching on a little rocket engine to keep the same distance continuously from the center, and then switch it off again when the shell comes back. Yeah.
Okay, thank you for the explanation. Are there further comments, questions from the audience? Yeah, then I would like to continue with another question. This is a positive formalism. You introduced there this very first example of P, exactly this P. But all these four gray squares, as shown on the left, these gray squares, they all depend on space-time, right?
Yeah, so of course, this is just some kind of illustration that is supposed to illustrate that these, what's happening here, I mean, either setting the switch on the instrument and also looking at the light of this other instrument are things that happen in space-time and that are localizable in space-time.
Okay, but then the fraction on the bottom right, there I have four squares, and the four squares, each of them depends on space-time.
Yeah, okay, so yeah, I should have drawn another of these diagrams here, because the point is that the squares on the top and on the bottom, I mean, the ones that are in correspondence are at the same space-time location.
Okay.
So what it means is that the one bottom here really at exactly the same places. So the switch is at the same place. Okay. And this one is at the place where there's here the green light, but it's undetermined.
Okay.
But yeah, so yeah, I'm sorry that this didn't come clear, because yeah.
Okay. No, thank you for clarifying this. No, it's.
But I hope, yeah, with this explanation, perhaps. And that's also the case, by the way. I mean, in these other examples here, it's the same. So the in is the box down here. This is the box in the middle. The out is on the top, and the one with the question mark is the same as the out box, but with a different label. So because in one case it means it's a fixed out state. In the other case, it means
it's all possible.
An undetermined out state, which is another way of saying that we are summing over all out states. But it's located at the top, at the same place.
I see.
And the same, of course, here, right? Yeah. So this box is this one, and this box is this one, and they're just different copies, which were on some of the copies we made changes. But the space-time location is exactly the same.
Okay, thank you very much for clarifying this. Yeah, and if there are no further comments, questions from the audience, or is there one? No, I don't think so. We thank you again, Robert, for this very, very nice, very interesting talk for us. And yeah, see you next week. Bye-bye.
Bye. Thanks for